All right. Strong, weak, strong, weak. Okay. Hello, Alicia. Hello, LA. So I gotta make my studio a tiny bit bigger. Yeah. What else? I need a book. Okay. I'm ready to roll. Hello, Bella. Hello, Feeny. Hello, Louisa. Thank you for joining me here on a late afternoon. Yeah. Hello, Amina. Till when is class? What is it? 4:15, 4:30 if we really get going and I can hold out that long. But 4:15 anyway, Amina. Hello, Chelsea. Hello, Anthony. Thanks everybody for joining us in a late afternoon. While we're gathering up, just hello, Anne Sophie. Just a point that I graded right before I am doing this with you, your AP FRQ test on equilibrium and other stuff, solubility, no, equilibrium. And I had a number of you that put in the wrong R value for PivNerd. So I just got to be a granny about this and remind you about labels. So for the R values, the only time you use this 8.31 value is if you got joules. It's joules per mole Kelvin. And you should have that on the given information when you take the AP, if you're taking the real test. So you don't have to put in the wrong one. Look at it, joules. If it's atmospheres, you're not going to use that one, okay? This one is 0.0821 liter atmosphere mole Kelvin. So, all right, so be careful with the R values. Several of you picked the wrong one. And you just have to look on the sheet or on the internet, just ask for PivNerd R values and just find the right one with the right label. All right. Hello, Alex. And let's begin, folks. Hello, Oscar. Good, good. And Oscar, I'm feeling okay, so we can figure out a time together. Do you have another shot for? Yes. Okay. So I got the AstraZeneca shot today, and I have a strong urge to eat tea and crumpets. No, I'm just kidding. No, it's a British shot, No, I'm feeling okay so far. We'll see how I feel tomorrow. That's kind of the big thing. So hopefully I can do our live stream tomorrow. And we're meeting, am I right, at 1, right? So 1 to like 2:15 tomorrow. So I think that's right. Yeah, so far I feel okay. I get another shot in June, but for AstraZeneca, I get most of the goodness out of it within 3 weeks. So a little after the time that I see you again in school, I hope, I will have most of the resistance to the virus, which is a good thing. It's a good thing. Hello, Errol. Okay. Yeah. So you should have your AP classroom quizzes back from last week already. You can kind of see how those look and check out some of the answers if you missed it. Several of you did very well on at least parts of the quiz. And yeah, the more practice, the better, right? I'm also going to try and open up, and Alicia, remind me of this. I forget. If I forget, I'm going to open up more of the available questions on the AP Classroom site. So if you want to work on some of those, please do so. Okay? Okay, let's take your questions. Are there some you'd like to ask about from chapter whatever in the book 2? Any you'd like to ask about? Now's the time where we can do some on the board and talk about them together. I hope that's as good as we can get there. So I'll erase my R values now that we talked about that. Oddly enough, on the quiz, I also had a few of you did not show any work, like you wrote 4.8 grams of NaCl, but it's just hanging out there. You gotta show work. I can't give you the points legally, and they won't on the AP unless you show some kind of work. If you can't fit it in, I mean, email me a copy of it, email me a picture of it, okay? Or whatever, but you can't skip it. End of sermon. Okay, any questions you want to ask about? Now's your time. While you're thinking, I'm going to look down and remind myself where we got to last time. Indeed, indeed. Good. No? Yes? Trying to have some ready for tomorrow too. If not, we're just going to hunker through. Okay, then let's hunker through. So, my people, we're just about done with the titration stuff. Now, Cheryl emphasizes a few different things than I do, but I'm just going to let you read through it and get some of her ideas. But the last type of titration I want to talk to you about is which one did we not get to? We did not get to the strong acid, weak base, or if we did, we just barely started it. So we're going to work on some of that now, okay? Strong acid, weak base titration. I'd sure like to see you do a titration lab, but I honestly don't know if we'll be back in the classroom. I don't know if we can get to it, which is a real pity. I may, at some point, photograph me doing a titration so you can at least see what it looks like with the equipment, all right? And there's Lola. Thank you. Good. Glad you joined us. Here we go. So I've got, and by the way, we figured this out last time, I think, strong acid, weak base. So the equivalence point is not at 7. We agreed that the strong one, the acid, wins. So the equivalence point, I'll abbreviate that, equiv point is on the less than 7 side. So we're going to use, and I think we did this in the class, in methyl red, all right, as our indicator. Just like I added a drop, a universal indicator when we did our demo with the buffer, you know, you're just going to add a drop of methyl red and then go do the titration, okay? All right, so what are we doing? We're having 50 milliliters of 50.0 milliliters of 1.00 molar NH3 is titrated with 1.00 molar HCl. HCl. Okay, so as you can guess it, we want the pH, part A, pH if 0 milliliters HCl added. In other words, we don't have a titration yet. We got a base problem. And so it's a KB problem, okay? So we got just a base. We got milliliters of NH3. So it's a KB problem. So I want you to think by doing what we did before. Okay, you ready? Here's the NH3. It's going to be dropped in water, like all solutions all year long. And can you type in and tell me what we get? So if I drop NH3 into water, what do I get on the other side? NH3 plus water. Write it down and then try and let me know. Please try and include the charges if you know them. You don't have to put them up above, but just somewhere. So NH3 plus water. What two things do I get as products? That's the KB 100 million euro question. And there's one already from Anne-Sophie. Good. Let's see if some others have sent stuff in. Sometimes there's a little lag time. I don't always see your answers right away. And there's another couple from a bunch of you, from Chelsea, Lola, and Alicia. And all of you are correct. Ding, 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 ding. Good. And it is indeed NH4 plus, because we're adding an H plus, and we're pulling it off the acid. So we're left with just, no, sorry, we're pulling it off water, pardon me, no acid yet. So we're left with OH minus is the other fella. Remember when we did that with salts? It's the same kind of thing. And it's a KB problem because I'm making some OH minus, right? So that's why I said it's a KB problem. Okay. I'm going to give you the KB right now. Okay, the KB, the number, is 1.8 times 10 to the negative fifth. Seems like we get that fairly often. I don't know why. It's just a random number, but it seems to keep coming up. Looks like an S. That's supposed to be a 5. I sure wish I drew better 5s. So let's do the deal. Ready? So the KB, we just got to write in symbols, is NH4 plus times the OH minus divided by, terrible brackets there, divided by NH3. And we don't include the water because the water is a you guessed it, liquid. So we don't include the water. Okay? Ute. Okay, you ready to play the game? You've done this so many times already this year, right? For every one of these that joins a water, NH3, I get one of these and one of those. Or for X of these, I get X of these and X of those. So let's plug in. Ba-dum. The KB number is 1.8 times 10 to the negative fifth and equals what on top, my people? On the bottom, it's 1 molar. That's easy. 1 molar NH3, 1.00 molar. What's on top of that sucker? Liquid. Thank you, Amina. Okay, what's on the top of the KB expression here, folks? Thank you, Alicia. And I'm going to guess some others are going to jump right in there too. It is indeed X and X or X squared. So can I help you? Can you get for me the X? And let me know what that is, my people, because I don't have a calculator handy. So all we got to do is what? That's 1. So just take the square root of 1.8 times 10 to the negative 8 for me. So maybe something times 10 to the negative third or whatever. X squared. Look at all those people knew that. Thank you, Louisa, Amina, and Sophie. Thanks, everybody. X squared was correct. All of you. Good. So take the square root of that. Let me know what you get. And I'll wait for you to grab a little calculator and do it. Square root of 1.8 times 10 to the negative fifth. I'm trying to get you as close as I can so you can see the board. Thank you. Okay, so Bella gets 1.34 times 10 to the negative fourth. Let's see if that checks with others. No, it does not. Okay, let's get some other answers. That's okay. It's all right to make a mistake. That's why I have lots of you punch it out. Okay, we'll try it again. Okay, so I got a 4.2 times 10 to the negative second, and I got a 4.2 times 10 negative third. Okay. Okay, we better agree on it. I'll go up to Amina. What's she got? She got 4.2 times 10 negative third. Let's go for that and see if it's right. 4.2 times 10 to the negative third. And now it's molar, isn't it? And that's what Chelsea got as well. Good. Yeah, it's negative third. Thank you, Alicia. Okay, great. So okay, clearly that's cool because it means I've got the concentration of which good stuff over here. You can probably look over and guess. That's the concentration of OH minus. Beautiful. So I can easily ask you to get the P. What am I going to be able to get? The P. And if you could get that P at the same time and send me a little number, take the negative log of that, and let me know what we get for the P. Thank you, Chelsea. POH. And let's see what we get for some numbers. Thank you, everybody. Amina and Sophia had that as well. What do we got for a number? Okay, back to Chelsea. She's got 2.4. Let's see if others get the same thing. I'll write it down here for grins. POH is 2.4. Let's see if others get the same thing. Just tell me if you do. That would be Swelleroonie. POH is 2.4. Thank you very much. Okay, so, but you know what? Look, this is a base. Why is it so acidic? Oh, I still got to get the what? And I bet I can do it mentally. I still got to get the pH. But we can do that in our heads, can't we? And you can do that on the AP. Look at that. You guys are way ahead of me, including Anne Sophie. She's got 11.6. That sounds right. Others get the same. So it is indeed basic, isn't it? It's greater than 7, 11.6. And others got the same. Thanks for Amina and others for checking it out. Good. Are we ready to keep going with this puppy? So it was a KB problem, B for a little bit boring, sorry. But now let's actually make it a titration. We're going to start adding acid. All right. Can you guess how much acid I'm going to add to make my first interesting step? So I'm going to erase this. How much acid will I add to get to someplace interesting? So B, question B. So I want the pH if milliliters of HCl is added. Let's see if some of you can guess. Oh, nobody's guessed yet. So I want to get to a magic spot. So how many milliliters am I going to add? I start out with 50 milliliters of the base, and I want to get to a magic spot. How many milliliters of acid should I add? It's the same concentration of acid, 1 molar, as the base. Alex, 50 would be too much because that would put me all the way to the equivalence point. But there's another magical spot I want you guys to know. All right. And Chelsea might have it. What is the magic spot? It's if I add 25 milliliters of the acid, 25.0 milliliters. Why? Why? Well, what does that give me? It gives me, so I got half of my weak base and half conjugate acid. So I got half NH3 and I got half that has been converted to what? NH4 plus. Remember we just did that in the KB problem? Well, same thing happens if I add H pluses to the NH3, I get NH4. So essentially I've changed, so I got half of the 50 milliliters are left, and the other half have been changed to NH4 plus. So thank you, Anne Sophie. Thank you, Lola. And it is a buffer. So I've got a weak acid and a strong, no, a weak acid and a weak base, basically. Okay, so it's a buffer. In fact, it's a what to what buffer, which makes life really nice. And I'm going to write the equation while you think about it. So the pH equals the pKa plus the log of B minus over HB. So why is this such a cool buffer? It's a hint to him buffer. Thank you, Amina. Thank you, Aunt Sophie. It is indeed a one-to-one buffer. So that makes life easy, right? In fact, it's all in the same vessel. So I've got the same number of moles and the same number of liters. The concentrations don't even matter. It's not going to be 1 molar anymore, by the way. It'll be 0.5 molar and 0.5 molar, but who cares? 0.5 over 0.5 is still another name for 1. So 1-to-1 buffer. 0.5 to 0.5 is the same thing. So the pH is just, you ready, my lovelies? It's the negative log of the Ka. Oh, what? I don't have the Ka. I got the Kb. Can I get the Ka? You bet, any day. How do I get the Ka? So let me do that in black over here. The Ka is what? Remember the Kw equals what? Ka times the, who remembers how to do that? How can I get the K, the Ka? The Kw equals the Ka times the, and do I really have to do this side thing? Yep, I do. But it's not a big deal. So how am I going to get this now? I want the Ka. The Kw is the Ka times the what? Thank you, Anne Sophie. Thank you, Alicia. It's times the Kb. So here we go. Kw is what? 1.0 times 10 to the negative 14th. Got to memorize that. It means water does not break down much. Equals the Ka, I don't know it, times the Kb. Oh, but I can divide by that. Why? Because I got it in the last problem. That was the 1.8 times 10 to the negative 5th. And now I'm going to ask you helpful people to give me the Ka value. It's going to be what, like times the negative 8th or 9th power, something like that. Could you do that for me? 1 times 10 negative 14th divided by 1.8 times 10 to the negative 5th, please. Let me know what you get. It's going to be times 10 to something. That is going to be to the negative something. And let's see what you get. Let's all punch it out and then compare, see if we get the same thing for the Ka. And then we can actually finish up this part B already, which should be beautiful. Okay, Bella's got 5.5 times 10 negative 10th. Let's see if others got the same thing. 5.5. 5.5 times 10 negative 10th. And I got a couple of 5.6. Okay, well, let's round it. I also lost a significant figure. I'm sorry I got a little sloppy, but let's just use 2 then for now. Thank you. 5.6 times 10 negative 10. So let's put it over here. So we want the negative log of that sucker, all right? Negative log of 5.6 times 10 to the negative 10th plus the log of all that is log of 1 is 0 power. So that's easy. So all it is the negative log of this. Can you guys get that for me? Can you get that for me? Let's see. So the buffer is going to be negative log of that, and that'll be the whole pH of the buffer. Let's see what we get. I'm going to wait for you to punch that out. Negative log of the Ka, what they call the pKa, right? pKa. And Bella's got it. I'm going to write it and see if others get the same thing. She's got 9.25 or 9.3. Again, I'm being a little sloppy on the rounding today because I'm in a hurry. Do others get the same thing? They are coming in. Oscar's got the same thing as well. Thank you, Oscar, for verifying. And it is indeed a fairly basic buffer, isn't it? A fairly basic buffer. Why? Because I've still got the buffer left over, and the only thing I've got with the NH3 is some NH4 pluses floating around. So it's a fairly basic buffer. Huge. Let's continue. Thank you. And others got the same thing. Thank you for checking. Let's do our third question, and now we'll get the answer from Alex, who said it earlier. So Alex, I'm going to now add how many milliliters of my acid? So we want to get the pH if milliliters of 1.00 molar HCl is added. All right, beautiful. Here we go. And how many is it? Alex knows it's 50. Thank you, Alex. So 50.0 milliliters. So now we're at the equivalence point, okay? Now we're at the equivalence point. And again, it's one of those that if I drew a graph, oh man, okay, maybe I'll do it over here. So we started out, remember how we started out? We started out with just base. And it's going to be kind of like this. I start out, so this is the pH. And I'm going to kind of go like this. And I get a steep part, but it's fairly short. Actually, it's not as steep as the other one. And the equivalence point here, oh, wait a minute, sorry. Okay. Okay. This is going to be right down here at 50 milliliters. This is going to be milliliters of acid. You'll see why I'm doing this, I promise. So this is going to be 50. And that's our equivalence point right up there. And at 25, and this is the cool thing, you're going to have AP questions like this. From a graph, 25 milliliters, when I go up there, that's going to be the pH of the buffer, which also equals the pKa. Doesn't it? So could you get the Ka from a graph like this? Yes. It's halfway to the equivalence point, and the equivalence point is where I got 50 and 50, don't I? So halfway would be 25 milliliters, and I go up to that, and the pH equals the pKa at a 1-to-1 buffer. So remember when I said that's a magic spot? That's a really magic spot. So at 25 milliliters on any graph, you can get the Ka, which is pretty cool. Yeah, which is the Ka for that thing. Is that right? I think it is. Yeah, it is. So we got the Ka for, yeah, that's correct. For the NH4 plus, that's the Ka. Okay, never mind. Let's go back and do the problem, shall we? Sorry, I'm hemming around here. So what's going on? Okay, let's think. So now I got NH4 plus, no, NH3. And can I just say from the HCl, I'm adding H plus. Is that okay between friends? All right. Because the Cl minus is a spectator anyway, right? And I've got NH4 plus. Well, you know what, gang? If I got 50 milliliters of this, and I add 50 milliliters of this, these suckers are gone. You know what I'm saying? They're gone. All I got left is NH4 plus. That's going to be our starting point now for the figuring out the pH. Okay, bear with me. And you might say, Mr. Weiss, how do you do this? I think about it with equations, and that's what I want you to do too. What's in there? Well, these are now gone. I've moved all of the NH3s over to NH4 plus. I've used up all the H pluses. They're gone too. And all I've got is NH4 plus. So now we got to do a new reaction. Do we? Yeah. But it's an easy one, okay? The new reaction is, hey, so what do I got? I got a beaker full of water or a flask full of water, and I got a bunch of NH4 pluses. So let's throw it into the water and see what could happen. Well, about the only thing that could happen is it could go backwards. So this got an extra H plus, so instead I could get what? I could get NH3. Do some of them really go backwards like that? Yes, they do. Weird, huh? And then what's left? Well, essentially, I've got I got to put the other item below here. So NH3 plus, sorry, that's the next item plus H3O plus. Oh, which is another name for the hydronium ion, right? Which is another name for H plus. Another way you could write this, if you don't like it, another way you could think about it that's maybe even easier is I could think this. All I got is NH4 plus, and if I throw that into water, I'm going to get NH3 plus H pluses floating around. And the H pluses, of course, will become H3O pluses, but that's what Cheryl would call it, but I'm going to just call it an H plus. So in other words, what I'm trying to tell you after this whole story is, my people, this is a Ka problem now. Ka problem, because I've got a weak acid in water. So just think that. I got a weak acid in water. So we're going to do it. Ready? Ka equals, you see how I do all these the same way? I get an equation, and then I write an expression, and I just keep doing it. That was it, Aunt Sophie, exactly, H3O plus. So my Ka is H3O plus, or I'm going to just cheat and say H plus because I'm lazy, times NH3 divided by NH4 plus. All right, you know the game. You know the game because we just played it. I don't know how many, there's a lot of these, and every one of these that does break down, I get what? X of these and X H pluses. So in terms of Ka, I'm going to get what? Ka going to be X squared on top, right? Divided by the concentration of NH4 plus on the bottom. Let's go back and look and see. Well, the NH4 plus originally came from this, didn't it? It was the NH3. What was the concentration there? It was 1 molar. But you know what? That was in what? 1 molar, but it was in 50 milliliters. How many milliliters is it in now total? And therefore, it won't be 1 molar NH3 anymore. It won't be 1 molar NH4 plus anymore, will it? What will be the concentration of the NH4 plus? Let's see if you can answer. It's not sitting in 50, it's now sitting in 100 milliliters of liquid. What would be the concentration of NH4 plus now that I've done and reached the equivalence point? And that, folks, is a really important thing. If you can do that mentally, that's what I want. Let me repeat. It was 1 molar. It was sitting in 50 milliliters. And it's been all converted to NH4 plus, but now it's sitting in 100 milliliters. Okay, and I got a couple of you have it. So Oscar and Chelsea, it's exactly half. So it's half of 1 or 0.5 molar. I'm going to write 0.50 molar just to keep another significant figure. And the Ka, oh man, we got the Ka. Golly, I'm so stupid. Let's put in the number for Ka, shall we? Hope you got an eraser there. The Ka we figured out in the last problem, right? Holy moly, the Ka was 5.6 times 10 negative 10th. So 5.6 times 10 negative 10. So I'm going to ask you guys to get X and let me know what that is. So you're going to take 5.6 times 0.5. Well, we could do that in our head, couldn't we? So it'd be like what, 2.8 or something like that? 2.8 times 10 negative 10th, and take the square root of that and let me know what you get. And Anne-Sophie, it's in 100 because we had 50 milliliters of the base, and we're now added 50. That's part B, we added 25. Part C, we're adding 50. So we're really in 100 milliliters of solution now, not 75 anymore. That was part B. Okay, somebody get X for me? My kingdom for an X. My kingdom for an X. Thank you very much. So I got from Bell and Chelsea. I got the same thing, and from Amina as well. I'm going to round that 1.7 times 10 to the negative fifth. Sounds beautiful. I'm going to put molar on there. And importantly, why? What is it we found? What's in our expression? Go back and look. Oh, that's the concentration of H plus. Beautiful. Can I get a pH? I say, can I get a pH? Could you please punch out the pH and let me know what you get now? I'm running out of whiteboard. I'm going to have to start erasing. I'll just put it over here. Okay, so you got the H plus. The pH, my people, would be what value? I'm going to wait and see. I got a question. Oh, no. Okay, that's the same thing. Yeah. And Sophia, I might have misspoke. When it was in 75 milliliters, I got to go back and think about that. But all I know is when I got that 25 milliliters, and Sophie, it's a 1-to-1 buffer. Okay, because I know they start out as 1 molar and 1 molar, and I've used half of it, so I got 0.5 molar. Oh, I know why. Because I only converted half of it, and Sophie, so it was not 1 molar of it anymore, but only 0.5 molar was left because I converted half of it. Here I converted all of it in part C, so it'd be 1 molar, except I got double the volume. So again, it's 0.5. So it sounds crazy, but both are 0.5 molar, but they were different chemicals, and Sophie. Okay, thank you. 4.8 looks good. And remember when we said the equivalence point would be on the acidic side because it was a strong acid and a weak base? It is. So methyl red was a good choice for our indicator. We want something on the acidic side, and that's methyl red. In other words, good. Well done. Well done, my people. Good. Okay, I'm gonna pause and got it. Okay, I'm gonna pause and do another graph like this. That's kind of big. Okay. So I want to make sure we don't miss that. So if I've got weak base, strong acid, then and this is the pH, it's essentially going to be, is that sloppy? Yeah, that's not bad, I guess. Maybe a little more rolliness. No, that's all right. It doesn't really matter. I gotta go down a little more. And again, this is milliliters of HCl. Okay? So again, let's mark some spots. So let's say we got, again, 50.0 milliliters. So at zero milliliters, basically I've got a KB problem, don't I? Because that sucker is a weak base. Weak base, that's all I got. If I had added milliliters, 0 milliliters of HCl, pardon me. If I go to the 50, let's go to that spot. So let's say that's 50 milliliters. So that's the equivalence point. And it's on the acidic side. So it's an acidic pH number. Okay, then there's really one that's interesting and we're talking about and important for my students to get is this one. It's 25 milliliters. So if I go up to that spot, boom. Right there is where I've got a 1-to-1 buffer. And the pH equals the pKa. Guaranteed you're going to get probably a multiple choice question with a bunch of graphs. And one of these will ask you to find the pKa. And all you do is you go down to half the amount of liquid that's been titrated. And once you do that, assuming it's like a strong weak or a weak strong, you can find the pKa and you can estimate it right off the graph because it's the same as the pH. Isn't that cool? And then if you're allowed to use the calculator, you could get the Ka, right, by just going what? So the 10 to the negative pH power, remember doing that, equals the H plus, which also would equal the Ka in this case. So that's a typical question, and I want to make sure that you are prepared for that. Okay? Ute, good. Here's another graph I want to look at with you. Ready? Conductivity. You can look up the units in Cheryl. I don't remember. It's some electron volt, whatever. So it's electrical conductivity. And it's conductivity of a solution due to the number of ions present. All right, you ready? For this one, we're going to do a strong. So example, HCl titrated with NaOH. So strong, okay? Now this is going to be cool. You're going to like it. So I'm going to make a graph, and on this side, it's going to be milliliters of NaOH. All right? Milliliters NaOH. Because that's my base, right? And on this side, it's not going to be pH, it's going to be conductivity. And again, whatever we measure electrical conductivity in, amperes, or it's probably some small unit, I want to say. And anyway, sure, we'll give it to you. It doesn't matter. What matters is the trend. And by the way, here's my beaker over here. Right now, my beaker's got what? It's got HCl, so I got H pluses, or H3O pluses if you want. And I got Cl minuses. Okay, now I'm going to start adding. So let's say we start with our conductivity being here, all right? Okay, now I start adding, so that's 0. I'm going to put 0 right there. Okay, so that's my starting conductivity of my HCl solution. Now I'm going to add NaOHs, and watch what happens. Think, Na plus and OH minus. So what's going to happen here? Some of the Na pluses are going to get grabbed by an OH minus and make what? Water. And when they do that, guess what's gone? Yeah, the H plus is gone. And the OH minus is gone. And instead, I get a few Na pluses, but I'm really pulling out some of the other ions. I'm also adding liquid. So I'm adding more liquid, and I know I'm adding Na pluses, but I'm getting rid of OH minuses and H pluses. So what that means is my conductivity does what? So when I first start adding NaOH, what happens to the conductivity of the solution? Because I'm making more water and I'm getting rid of both H pluses and OH minuses. What happens to the conductivity? Remember, the more ions, the more conductivity. Amina's got it covered. Yes. There'll be less conductivity. It decreases. It's okay. I'm just giving you a hard time, Amina. Okay, so conductivity goes down. Why? Because these suckers are being taken out. I'm losing H pluses until I get to, let's say I got 50 milliliters, all right, of HCl. Well, watch what happens when I get to 50. So it decreases. Now, I get to 50, and all I got in here is I don't have any H pluses. I've got a lot more liquid. And I've got Cl minuses and Na pluses. But they're not all that concentrated. So that's why the conductivity is so low. There's less ions. I'm going to write this down here. There's less ions per liter. That's why the conductivity has gone down. Less ions per liter. But, and we're doing what? This is 1 molar, sorry, and this is 1 molar. And right here, I'm at the equivalence point. Yes, I did, Anne-Sophie. Okay. This, guys, I didn't want to start right at that axis. So let's just say we're starting here. Okay, so it goes down, down. Now I'm at the equivalence point. Now I've converted at the equivalence point, I've converted all of the H pluses and OH minuses to water. So now I'm going to keep adding. I'm going to keep adding until I get out to 100 milliliters of NaOH. What's going to happen to the conductivity now that I add more NaOH and I'm not pulling H pluses out of the system because they're all gone? So now you've hit the equivalence point. What's going to happen to the conductivity as I add more NaOH? It's kind of a weird question because I know we haven't talked about conductivity much, but it's on the AP. That's why I ask it. So I'm going to add more NaOH, and I'm not going to take out any more H pluses because they're all gone. So now I'm going to have not only these, but I'm going to have some OH minuses floating around in there as well with more Na pluses. And you guessed it, Chelsea guessed anyway, it's going to now increase. So it's going to go back up. Isn't that kind of cool? So you get to a minimum electrical conductivity at the equivalence point right there. Isn't that wild? And then after that, it starts going up again because you're not making more waters, but you are adding more ions to the solution. That's what I wanted to show you. Exactly. So it's going to increase. Yeah, the equivalence point will be right there at 50. That's right. Right there at 50. So above that, no more making water. So I stop losing ions and I start gaining ions, which gains in my conductivity reading. Yeah? Okay. Okay. Thank you. Penelope, I know you told me. It's okay. It's okay. Just watch the rest of the video. I'll try and save it. Hopefully I don't crash. And then you can watch the earlier part. Okay? All right. So, good. Okay, I'm going to do two things, my people, while you're thinking. I want to first answer any questions you got. Second, I want to thumb through Cheryl and see if we covered what I need to in Cheryl. Again, some of the items I'm going to leave to her, but some we've already done. Like 6.1 is all about salts. We already did that, okay? Chemistry of buffers, we did that beautifully. And she uses the Henderson-Hasselbalch equation. We've used that a whole bunch. And so I'll leave that to her. That's dandy. That's 6.2. 6.3. We're talking about titrations, and you and I just did a bunch of that. So we're looking lovely. We've done 6.3 with Cheryl. And 6.4 is a closer look at titrations. And we talked about indicators, so we've done that with you. Now, Cheryl has a bunch of indicators. I don't care. The main three you need are the ones I gave you. Methyl red, phenolphthalein, just kidding, and the bromothymol blue. Those three that we made a little table of, those are the three to know, okay? The other ones she talks about, it's nice, but you don't have to know them. Halfway to equivalence point, beautiful buffer. We did that. We did that a couple times. Life is good. Lots of graphs. We did that. Buffer region, equivalence point, beautiful. I'm so excited. He's sitting in my basement. Okay. And then the last section, 6.5, non-metal and metal oxides in water. We had this in 9th grade, and you're not going to remember it, so I'm going to tell you now. Okay? Here we go. So this is page 415. I'm going to give you the knuckles down, easy approach. page 415, and this is section 6.5. If you had me in 9th grade chemistry, we did this. If not, we'll do one on paper. Okay, if I got a non-metal oxide, and I drop it in water or mix it with water, some of them are gases, I get what? Okay, ready? Let's do one. SO2, and that's a gas. Kind of a smelly gas. And water, like water vapor, forms. Now, it's kind of funny. You just add it up. Ready? Check this out. H2SO3. What kind of compound do you suppose that is? H2SO3. What do you think? H2SO3, going to be what sort of compound? I put the H's in front for a reason. What will it be, folks? H2SO3 is waiting for your response. Yeah, we're still working. Sometimes it takes a while before when you tip in. Now I got a bunch. Oh, I love it. I get it all at once. Good. Thank you, Chelsea, and Oscar got it, as well as Anne Sophie and Amina. It's an acid. Alicia as well. Good. Everybody. So I get an acid. And generally it's a weak acid, just so you know. Okay? But that's kind of cool, isn't it? So this is the general trend you got to know. Okay? Put a box around it. If I got a non-metal oxide and I add water, I get an acid. This, my people, will be in stark contrast to the next thing we do. And then that's all of 6.5. It's just two things, two items, okay? All right, you ready? Draw a line. Now let's do another. You guessed it, Chester. Now we're going to take a metal oxide. You know where the nonmetals are, and you know where the metals are on the periodic table. And add that to water. And I bet you'll never in a million years guess what we make. Let's do one just to prove it. Okay, ready? Here we go. I'm going to take BaO, which is actually a solid, and I'm going to throw it in some water. Chuck it in there. See if you can guess what we're going to make. See if you can guess what we're going to make. What chemical will we make? And in the meantime, I'm going to circle this because this is going to be super important too. A metal oxide plus water makes a what? Thank you, Mina. It makes a base. Super. Now let's make our base. Ready? Make me the formula down here. Can you make a base formula out of this? It's BaO plus H2O. Make it into a base. What sort of formula would I get? Hint, going to start with Ba. Make it into a base. What formula will it be? Hey, you guys. All right. So thanks. Anne Sophie's got it. And Amina, you're close. It's just a Ba2 plus, so it needs two of those things. So I got two O's, boom, boom. I got two H's, so I get two OH's. Look at this thing. Now that's even a strong base, so I can't say a weak base forms. That's actually one of our strong bases. How cool is that? So that's essentially section 6.5. So she makes a big deal out of it, but really it's those two types of reactions are the main things out of that section, all right? Non-metal oxide plus water makes an acid. A metal oxide, remember, periodic table, non-metals over here, metals, all these guys, okay? So metal oxide plus water gives you a base. Isn't that beautiful? Okay. Shall I have you do a couple? You ready? Okay, here we go. Sharpen up your pencil. Your turn. Okay, so fill in. It won't be exactly the same. You'll have to think, but you can do it. Just balance it. And then we're going to do NO gas. My dad used to say that gas to me a lot. Plus water forms what? Okay, can you fill in either one? So put your thinking cap on and think some good AP thoughts, and let's see what you come up with. Just remember our trends, non-metal oxide and metal oxide. What do they make? Try and build it, okay? Isn't that kind of cool? While you're doing that, I'm going to check Cheryl out and make sure I didn't screw up something. All right. Hey, nice. Thank you, Penelope. Thank you, Chelsea. And indeed, the first one is NaOH. Good use of your charges, right? Na is plus, OH is minus. And as you probably guess, you got to put a 2 in front, don't you? Like Penelope and others did. Yeah, exactly right. So that's going to make a base because it's a metal oxide and water. Yeah, good. Okay, crank out the other one. Crank out the other one. Exactly. Looking good. Yeah, so I got it from a couple of you already. I got a H2NO. Does that work? NO2? Then it doesn't balance, does it? That's not an H, that's an N. I think I got to balance this different. Let me look at Cheryl, because that's not balancing right. It's NO2, but that's only -1. Oh, yeah, that's it. That's it. All right, so, sorry. Let's see, maybe you got it right. Yeah, something like that, right? So it's probably going to be HNO2. And we're probably going to have to rebalance this somehow, won't we? So I got an NO2, I got the O, and it might give like some hydrogen gas off. Let me see if she's got this one. Hold on, don't panic. She might have this one already. Oh, okay. She says this. Sorry. So she says it works out better if you do NO2. So go ahead and add a 2 there. And you get HNO2 and you get some HNO3. Now that's kind of a harder one. So you get some of both. Let's see if that balances. So we'd have to have 2 of these suckers. So I'd get NO2 and NO3. That's right. Yeah. So HNO2 plus NO. So I get 2 different acids, don't I? Yeah. Here's another one like that. You ready? CO2 plus water. You might know this one already. What do I get? H2. In fact, we had this one in our lab that had to do with the oceans, our question on the metal cation lab, right? Remember that? And that's an acid as well. These have to do with a little problem that occurs sometimes called acid rain. So when companies make a lot of NO2 or CO2, it mixes with the clouds and can make acid rain. Not so good. It was a bigger problem in the 1980s, especially in Eastern Germany, not so far away, and the Eastern US. Luckily, there's more scrubbers to take the CO2 out. Well, at least the carbon, the unburned carbon out, but it's still a problem today. Huge. Good. Questions from you? Let me look and see. H2CO3. Thank you, Anne-Sophie. Good catch. Carbonic acid or Kohlensäure, if you've been in Germany a while. And it's H2CO3. Good catch, Anne-Sophie. So carbonic acid is made. That's the same stuff in your drinks, right? In your bottle of Diet Pepsi or whatever you're drinking. It's Kohlensäure, right? Kohlensäure. Okay, we doing okay? Okay, so what we're going to do is we're going to start the last chapter, at least a little bit, okay? Don't get all panicky. In fact, we should yell, hooray, hooray, they cried. So it's about redox reactions, some of which we had already, so you won't be completely in the dark. We're going to review some stuff we said. So this is chapter 7. Does Cheryl call it electrochemistry? Let's see what she calls it for grins. Redox reactions. And again, you guys already had some of this, so it's not a bad place to start. Okay. I may do a demo in school and mail you the YouTube to watch, just as a warning. Let's review. Electrode, some terms here, is a metal or carbon is sometimes used. Stick. And it's used, well, okay, let's just see, it's where the electrons are gained or lost. Gained or lost. Okay, so let's review a little bit. If I got a cathode, attracts cations. Meow. So in other words, the cathode going to be what charge? Right? If it attracts cations, it itself better be a negative charged like rod. Okay? And if it attracts cations, it's going to feed them electrons. So at the cathode, we got these cations come up. Here, let's just put a little symbol. So here's a cathode, right? Here's my solution. Here's the cathode. It's negative, right? So here come the positive guys. Let's make it copper. Cu plus. Let's make it Cu2 plus because I can use that later. So these guys come up, and what they do is they grab onto electrons. So they gain electrons. So the Cu2 pluses say, oh, look, it's negative. Beautiful electrons. Mind if I have two? I'm 2 plus. I'd like to have 2 electrons, please. In fact, we're going to write that equation. You ready? So Cu2 plus is going to want 2 electrons, duh, to become neutral and become Cu later. And now it's going to be a solid. Before it was aqueous. And interestingly enough, once it becomes a solid, it sticks to this cathode. Let's make my cathode a funny shape. So the cool thing is it attracts cations. These gain electrons. Often, if it's a metal, the cathode gains mass. It gets heavier because they grab on here and they stay on and they coat the thing. So often the cathode gains mass. Now, if it's a gas or something, it's not going to grab on. So don't write that in stone, but often the cathode gains mass. All right? So we can write cathode and we can write gain electrons. Cathode gain electrons. The other thing we got is the name of the process, and the process is called reduction. We had this earlier in the year, didn't we? Reduction means the charge goes down. So we gain electrons. I'll get your question in just a sec. Gain electrons, so the charge reduces. That's why it's called reduction. So if I got electrons, I'm going to get more negative. My charge goes from whatever to something more negative as a number. So charge reduces. Let's see if that happened with our copper. I know. I'm using every bit of my board today. So look at that. My copper was at 2 plus. It went to 0. All metals are 0 if they're solid. So it reduced from 2 plus to 0 is going down or reducing. So reduction really is gaining electrons and the charge goes down. Let's see what my question. What does it say after the gain electrons? See. So it doesn't say anything. Cathode, a tricky way to remember it, entropy is gain electrons. And then over here I got cathode. Okay, these gain electrons. Often the cathode gains mass. And then I wrote reduction is the process. Reduction means gains electrons so that charge reduces if we gain electrons. And that, of course, is half the story. Next to the cathode drawing. Over here, I've got Cu2 plus 2 electrons forms Cu solid. Maybe it's a little glary where I had it. Cu2 plus 2 electrons makes Cu solid. And over here, I got gaining electrons. That's what the cathode is doing. And then I got my Cu2 plus. It's supposed to be one thing. Cu2 plus is attaching on here in the solution. It's attaching onto the cathode stick. Okay, it's usually a stick of metal. Or it could be a piece of carbon. Good. Okay, I'm going to erase this and we're going to do not reduction, but up in the sky. It's a bird, it's a plane, it's oxidation. And so it's just the opposite if you think about it. What time do we end today? I think I'm going to go and finish up oxidation. I actually said 4:30, and I need one of your days to go a little longer. Let's finish up a little oxidation, and then we'll call it quits, okay? Give me at least 5 more minutes, all right? Okay, let's do it. So oxidation is if we lose electrons, okay? So that's kind of the process right there. And I do it at something called the anode. So an anode attracts anions. And so if I have an anode, to attract anions, it's got to be positive. So my anode is positive. It's kind of weird. Just remember it attracts anions, okay? So what they do is, let's take like, who did I do? Who did I do here? Let's take Zn. Let's make this thing out of Zn. So what happens is the Zns give off their electrons and become Zn 2 plus. And then they float away. So I got a Zn solid, which is part of the anode here. Zn solid gives off 2 electrons plus a Zn 2 plus. And it floats away. It's aqueous. So often the anode does what in terms of mass? Often the anode does what? Often the anode does what in terms of mass? I know I'm pushing the envelope. It decreases, thank you. So it loses mass. I know you're tired. I kind of am too. I think that shot's getting to me a little bit. But in a couple weeks, I should be pretty good, right? Got my AstraZeneca. All right, so the anode attracts ions and often loses mass. So literally pieces of this fall off over time into the solution, and they become Zn2 pluses, all right? And of course, I got to have both processes happen. Both processes happen together. So both processes happen at once. If it's exothermic, and we're going to stop right after this, I promise. If it's exothermic, so it gives off energy, it's called a voltaic cell. And that, my friends, is what we're going to draw next time. Named after the great Italian Alessandro Volta. Yeah, good. So we're going to draw a voltaic cell next time and more or less put the anode and cathode together and see how this works. If I can do it at school at some point, okay, I'll make one and send it in a video if we can't see each other in person. Okay, thanks for sticking with me, everybody. Oscar, write me an email. Everybody else, I wish you good health. I'll see you tomorrow at 1 o'clock, and let's try just do an hour and a quarter then. Okay, one and a quarter hours. So we'll go till 2:15. I think we're doing okay for that. Okay, stay healthy out there and take your vitamins. Bye-bye.